Welcome to this presentation about Gprofng, the Next-Generation GNU Profiling Tool. My name is Ruud van der Pas, and this is joint work with Vladimir Mazentsev. I will be presenting today. We both work in the Oracle Linux Engineering Virtualization Organization, and within that we're part of the compilers and toolchain team. And I'd like to thank the organizers for inviting us to give us this opportunity to talk about Gprofng. We're very excited about our tool, and I hope to share a lot of information with you in the time that I have, but I also would like to leave enough time for Q&A. So let's get started. I want to show you many examples. The goal of this talk, as far as I'm concerned, is to show you the kind of things you can do with Gprofng, how it can help you analyze the performance of your application. So after a brief introduction, we'll have a demo and lots of examples. I can't go into a lot of detail, but please bear with me. I hope you'll find it useful to see the kind of things that can help you analyze the performance. If you want to know more, we have a repo. I'll get back to that in a second. And that's a mini tutorial in tech info format that explains a lot of the things that I'm talking about today. In the end, I want to share with you a bit of the things we're working on and our plans for the short term. It all started, at least to the outside world, on August 11, 2021. Of course, we've been working on the code for quite a while by then, but at that point, we submitted our code for review, and we sent it to the binutils alias because we would like to be part of that collection of software tools. So this is the very first email that we send out, and all those emails are archived in case you'd like to look it up. And that was in August. Then, to our delight, on March 9, we got the approval to be included in binutils. Of course, between those two dates, a lot of work had been done, and we definitely want to thank the reviewers for all their work and their patience, working with us and helping us to get there. It's very exciting, so that means from now on, Gprofng is part of the binutils repo. So you can go to the development repo, and it'll be there. And when the next official release comes out, Gprofng should be included in it. But again, you can download it today. You can clone the repo today and get started if you like. And here's how you would do that. I put this in for reference, so you can see how you can clone the distribution of binutils. Again, that's the development version, and you'll get your copy of Gprofng included. A little bit of history. I'll keep it short. This tool has a long and interesting history, but I want to pick it up when it was called Oracle Developer Studio Performance Analyzer. That was the name of the tool. And it had been developed for over 20 years. And in doing so, it picked up a lot of internal and external users with real-world applications, pretty ugly applications, and that has helped to make the tool more robust and more mature. For a long time, the focus was on the Spark processor, the Studio compilers, and the Solaris operating system. But actually, for over 10 years, there was already work done on supporting x86 on Linux. And what we did, we took that source tree, and that was the basis for Gprofng. But we did a lot to it. First of all, we created the standalone version, so it was taken out of the Studio context. We modified the code to be compliant with the GNU coding standards. We also changed the build process to be compliant with the way you build other binutils components. We added a port to ARM. That's kind of interesting. That's fairly new, but now you can make a profile on ARM as well. We found and fixed several bugs along the way, and we redesigned the user interface to better suit our needs. So what's Gprofng? It collects and displays application-level performance data. So it's a tool that helps you better understand the performance of your application, written in C, C++, Java, and Scala. We fully support the GCC compilers, and there are many processors out there. So we have support for processors from Intel, AMD, and ARM. I don't even want to suggest that we support all of them, but we try to stay current and support reasonably up-to-date processors. One of our key features is that you don't need to recompile the code. I'll get back to that later, but you can take your production binary, the code you're running in production, and you can get a profile for that code. So you're actually really profiling what you're running in your production environment, not some different binary. I think that's a very strong point. So the profile, any work you do on tuning it is of immediate benefit to your production binary. We have full support for multi-threading, codes written using Posix Threads, OpenMP or Java Threads. You can profile them and get information at all sorts of levels regarding the multi-threading. So how does Gprofng actually work? It's a two-step approach. First, you collect the performance data using our tool, and then you're going to analyze or display that information. So it's a two-step approach, and with one run, you can get a lot of information already. And I think that's one of the nice features of this tool. You do one performance experiment, and you can get information at the function level, at the source level, disassembly level. You can look at multiple threads if it's multi-threaded. So with a single run, I find that I already can get a lot of insight, which will set me on the path to start digging deeper into a certain area of interest. There are three things that I want to sort of call out that I think are really good to know about. First of all, we support scripting, so you can write all your profiling tasks. You put them in a script. I do that all the time. I never type in the things that I'm going to show next. I put them in a script, and in that way I can completely automate the generation of the profiles. At the end of the run, I'll have the profiles in the files, and I can start analyzing them. We support filtering, so you can zoom in on an area of interest in the data that you have. And I think a really cool feature is the comparison of profiles. When you think about it, profiling is about comparing. You have a good run and a bad run, and you want to know what's different. That could be multi-threaded, that could be single-threaded. You want to know what's different, and we fully support that through the comparison of profiles feature. And I'll have an example of that at the end of this talk. The name Gprofng sort of begs a comparison with the good old gprof tool. This is far from complete, but just to give you an idea like what's different, a little bit of a comparison. First of all, the underlying technology to collect the data is rather different. For gprof, you need to recompile your code. It will then instrument your code, insert calls to collect the performance information. You don't have to do that with Gprofng. We use the sampling technique that I'll explain next. So again, you can take your existing binary, no need to recompile. So take your production binary and start profiling. Gprof has fallen somewhat behind in terms of supporting modern kind of features. So we have support for shared libraries and multi-threading, for example, and I think that's where Gprof is actually rather weak because it didn't keep up with that. You can't do a lot of customization with Gprof, while Gprofng you can do a lot of customization and scripting to really make it suit your needs. I don't think Gprof has any support for filters, while we have filtering to, again, zoom in on the area of interest. You can't do comparison of profiles as you can do with Gprofng. And Gprof does not have support for event counters, while we have support for that. Now, to be honest with the latter, that's very machine-specific, very processor-specific. We're a bit behind in supporting the latest processors. And some we have, some we don't. So that's active work in progress, and we're trying to close that gap as soon as possible. So here's how the sampling works. It's called statistical call stack sampling, and here's how it basically works. It's a simplification, of course, but while the program is executing, we stop it. At some point, we stop it. We record things like the program counter and all sorts of other information we care about. Then we let go again. And by default, 10 milliseconds later, we stop it again. And that sampling rate is actually one of the tunables you have when doing your data collection. You can change the sampling frequency. So you sample all that information, and that allows us to show you, for example, an overview like shown here, where your program is spending the time, and of course also including a percentage of that. So that's basically how it works. And one of the reasons I want to show this slide, well, actually two reasons. First of all, this is how we can do the magic without not asking you to recompile the program. We just take the binary you have and we stop it at regular intervals. The other thing I want to point out, though, is that it's a sampling. So it's not 100% reproducible. If you run the same profile job again, the numbers probably slightly different. What we find is that those differences are usually pretty small. So in the order of like a couple of percent. But don't be alarmed if that's the case, because that's in the nature of the beast. So regarding the user interface, we've defined the following, that all commands start with gprofng. That automatically makes things unique, so that avoids collisions with other commands, for example. Then you describe the functionality that you want to have, and depending on that, there could be qualifiers and options. For example, to collect information at the application level, gprofng collect app. To display the information, you do gprofng display text. To archive your directory, you use the archive command. Currently, we have 5 commands that we support. Collect app to collect the data. Display text will display the performance data in ASCII format. There's an archive feature that will actually allow you to sort of freeze the configuration. We'll copy libraries into it, so that if your system changes, you still have a snapshot of the system as it was sort of when you did your experiment. We're not copying the whole system configuration, of course, but for example, shared libraries that you used will be copied into that directory. So if they change in the meantime, you still have access to the old one. Display source is not very rich at the moment. We have some ideas on that, but currently what it does, it displays the source and disassembly of an object file. So you give it the name of an object file. It will show you the source code interleaved with the disassembly. Display HTML is included, but it's not really functional at the moment. I'm working hard to change that. And what it will do, it will generate an HTML structure so you can load that into your browser and do the data navigation through the browser. Before I continue, I need to explain an important concept called inclusive and exclusive metrics. A metric is something that you record, like a CPU time, cache misses. So let's stick with CPU time for now, but it could be anything. So the inclusive metric includes all callees underneath the caller. So you're at a certain point in your call tree, and you're measuring CPU time. So all the CPU time underneath that function is being accumulated. So it's everything will go into that. So that will allow you to find the most expensive path in your program. That's the one with the highest inclusive metric. But then you want to know within that path who's spending most of the time. So that's why there's also an exclusive metric, which will give you the pure time or metric spent in that function outside of calling other things. And that will in a call tree will give you the one sticking out regarding the CPU time or cache misses or any other metric that you select. And here's a simple example. I have a bunch of functions here, and the orange one, let's call it A, is calling everybody else, and this is showing their respective times. So if you would compute the inclusive and exclusive time for that, you would see the following. A is calling everybody else, so its inclusive time is 75. Its exclusive time is 10. B is what we call a leave routine. It's not calling anybody else, so its inclusive and exclusive times are the same, 20 seconds. C is taking only 5 seconds by itself, but it's calling something that takes 25. So the inclusive time is 30 and the exclusive is 5. So what this tells you, for example, is that the path to C, in that path, C itself is not important. The one it's calling is more important. And likewise for the other functions. So that's the reason why there are two metrics, inclusive and exclusive. And by the way, if you don't want to see any of these or one of those, you can easily exclude them from your data views. So it's time for a demo. I just want to show you, in this demo, I want to show you how easy it is to get a profile on your screen. And I want to show you how you can make a profile for your own application using Gprofng. My application is a simple matrix vector algorithm parallelized with Posix Threads. And the way I run it is I specify the matrix sizes, the number of rows and columns, and the number of threads that I want to use, which is 2 in this case. So the program runs as usual. It ran to completion, all is well. The question is, how do you make a profile out of that? Well, it's really easy. You run the program as before, same environment variable, same settings, nothing changes. The only thing you do is you're going to run it under control of gprofng. You tell it what you want to do. In this case, I want to collect performance information on my application. So gprofng collect app, and then the way you run your program. When you do that, you'll see an extra line creating experiment directory test.one.er and a process ID. The test.one.er, that's a regular Linux directory that has the internal information for gprofng to show you the performance data. And that's clearly a default name. If you would run this again, you would get a test.2.er, test.3, and so forth. And of course, you can change that name if you want. By default, we never overwrite an experiment directory, so we'll keep on numbering. But again, you can use your own name for the directory, and that's what you use in practice to give it a more meaningful name. In any case, we have our test.one.er, and now we can start doing the analysis. So we start gprofng again, but this time I want to display the information. I want to do so in ASCII or text format, and I want to analyze the information in that directory. And here's how you do that. Now, what happens when I use the command this way, I get into an interpreter mode, an interactive mode. I can give commands and I can sort of navigate my way. But to be honest, I never use it this way. So I'll get out of that, because the way I like to use it, and I would sort of recommend you do it that as well, is you give the commands at the command line as you invoke gprofng. So here what I'm doing is I'm asking for the function information. I want to get the function overview for that experiment. And that's how you do it. And this is what I get on my screen. And what we see that the two columns, the exclusive and inclusive total CPU time with their respective values and the name of the function. The first line requires a little bit of explanation. That's called total. You will always see it. And that's generated by gprofng. That has the total value for that metric, in this case, the total CPU time. So what it tells us that the total job took 1.691 seconds. And out of that, 1.611, so pretty much almost everything, was taken by a function called mxv_core. So if we ever want to do some optimization, mxv_core is the one to look at. So that's a very basic but useful profile, and the steps I've been showing you are really all that is needed to get it. First you collect the performance information using gprofng collect app, and then you display the information using gprofng display text, and that's all that it takes. Now, there's a lot more to say about this, and there's a lot more information that you can get out of even this simple test.one.er directory. And for that, I'll switch back to the slides and I'll show you lots of examples of all the kinds of information you can get. So let's go back to the slides now. Well, that was the demo, and again, I hope you found it useful. And I want to show you examples. I want to show you how to get a basic profile, which I already did in the demo, but I'd like to have it on the slides as well, easier for reference maybe. I want to show you how you can display function, source, and disassembly information. I want to show you a little bit about customization, scripting. I want to bring under your attention the call tree and call the colleagues view. I want to give you an idea how we support multithreading, filtering, and comparison of profiles. So here's how you get your basic profile. If this is how you run your program as usual, and you've set your environments and whatever you need to run your program, all you need to do to get a profile is do the same run, but now under control of gprofng collect app. And the defaults, I think, are pretty well chosen. If you would do this, you would get a new directory that we call the experiment directory. And as I explained in the demo, the default name is test.one and so forth, but you can change that name. But that directory has all the performance information that we care about. So the next step is to analyze that information. And I use the functions command. I want to stress that what I'll show you is the single commands on these kind of examples, but you can combine them. You can get all the information by having a long line with the functions, with the options that you specify. So don't be fooled by that. You can make them as long as you want. I'm just doing that here for layout purposes. So if I want to get a function overview, all I do is do this, and then I get this kind of overview. We see the exclusive and inclusive times shown. I already mentioned the function total. Total is an important metric. It accumulates the total values of all the metrics like cache misses, CPU time, and for that column it shows you the total value and then the breakdown over the individual functions. So that's the purpose of total. A nice little thing is called lines. With that you get the hot source lines in your program, so the ones spending most of the time or whatever metric you have specified as being important. So in that way you can quickly find out at the source line level where things are happening. If you want to get the source line overview, you use the source command, and for that I need to add a little bit a word of warning. You have to compile with -G for this overview to work. Pretty much every other overviews work, but in order to do the mapping from the information we have back to your source code, we need to have the code compiled with -G. And I hope you did that. And if you've done so, you will see an overview like this. We have the various metrics that you used, whatever you used, followed by the source line. The red coloring is mine, and the tool won't do that. But there is a marker. The two hash symbols in the leftmost column, they mark the most expensive lines in your code. So if you have a long listing, you can easily search for that to find the most expensive part in your program. And here what we see is those are the statements at line 36 and 37, taking a lot of the time. You can go down a level lower, which can be really useful because at the source level it's not always easy to tell you what happened. And you can go down to the instruction level. Same thing, again here the color coding is mine. Note that it gives you the line number. So what we see is line 36 and 37. Those are the red ones that I colored. And that's apparently where things are really happening. And you can find the most expensive instruction. Or given, if you know how processors work, it's sort of near the most expensive instruction. That's because of things like out of order. And superscalar, it's not always easy to pinpoint exactly the right instruction. But again, this tells you the area of interest at the disassembly level where things happening. A little bit a trivial example of customization. Still, I want to mention it. Let's say I don't want to see all those lines in my function overview. I can use the limit command to limit the number of lines to 5 in this case. And I can also redefine the metrics that are shown. So that I use all the time. So I select what I want to see. And in this case, I want to see the total CPU time. I want to see that as an exclusive number, only exclusive. I don't care about inclusive. I want to see the time, that's the dot, that's the absolute value, but also the percentage. So that will give me an overview like this. I only get 5 lines, and it will give me the top 5 in my code. And I can see that, for example, mxv_core takes 95% of the time, which is fairly obvious from the numbers, but it will give you an immediate percentage, which is quite useful, I think. Scripting, I use it all the time. So I'm not typing in all those commands. I put them in the script. So here I'm defining the metrics. I want to first see the name of the function, then I want to see the inclusive metrics, and then I want to see the exclusive metrics. By default, the first metric selected is the sort metric. That's not what I want. I want to sort according to the exclusive total CPU time. So I define the sort metric. I want to see the top 5, and I want to see the functions. And this is how you invoke it. There's a script option on the display text, and you give it the name of the file, and that's it. By the way, you can still have command line options here as well. So you can mix and match with command line options. In practice, I put everything in a script, but you don't have to do that. And this is the kind of overview you now get. I get the inclusive and exclusive metrics with their respective percentages. And as I said, that already can give quite some insight into where the time is being spent. Another example of customization is the name of the experiment directory. We have two options for that, lowercase o, uppercase O. Lowercase o will not overwrite an existing experiment directory. That's a safety net. Personally, I don't like that very much. I just want to blow away the old directory and don't have to remove it first. So I use the -O that will remove any existing experiment directory with that name and create a new one. It's just a convenience, I think. But be careful that it will remove whatever you had with the same name. There's a lot more you can do to customize the behavior and the output. You can set the sampling granularity. You can add labels to an experiment, so up to 10. So that information can be retrieved. So if you want to do some sort of documentation inside your experiment, you can do it. I already mentioned the archive command, where you can archive and sort of package up your whole kind of code environment and have that in the experiment directory, so that if you do a later analysis and meanwhile a shared library has changed, you'll still be looking at the library you used at the time you did your experiment. So that could be quite useful. And I want to show you the kind of the call tree features we have. There's a call tree command to show you the dynamic call tree. It shows you what was executed and how much of the metric was spent there. And let me show you an example. All you need to do is use the call tree option. So with that command, I get the following output. I see the attributed total CPU time, so how much CPU time was spent, but essentially two branches here. The first one, color-coded pink here, is the multi-threaded part. So that's all under start thread. That's the parallel part of my code. And the second one is the sequential part. So that was outside of the threading environment. So the sequential part, and you can see the breakdown of the times. Now this is a very simple example. This is a more realistic example where I also use some hardware event counters to, for example, measure how many instructions were executed and the number of last level cache misses. So you'll get that included in your call tree as well. So that, again, that will help you identify where resources go into, where time is spent, where cache misses go, and so forth. A related option is called caller callees, which will tell you for a given function who's calling it and who it is calling. So for my matrix vector application, the very simple, I color coded the target, which is marked with a star, blue here for easy identification. So we see that main is called by the system startup routine, no surprise, and it's calling 3 other functions. And we see how much time they take. And we see that malloc, for example, is called from 2 of my functions, allocate data and check results. And malloc itself is calling, for example, int_malloc. So that's the caller callees. It will give that for every function in your program. Multithreading. We have quite, I think, rich support for multithreading, and I'm going to want to show you how that works. First of all, there is no change. You run your program as usual in the multi-threaded environment. As far as gprofng goes, there's no distinction. You don't need to do anything special. You just do your data collection as before. Now, in this case, I'm going to use 2 threads, and I use the -O option to give the experiment a more meaningful name. And one of the commands that I really like with multi-threading is the threads command that will break down the information across the threads. So now I can see that I have 3 threads, and I see how much CPU time they took. And this is, for example, a great way to find load balancing issues in your multi-threaded application. Here we see what I expected. I used Posix Threads to parallelize this program. I have a main process that's sort of the driver. The driver doesn't do much. It's calling the matrix multiplication on 2 threads. So what we see is both thread 2 and 3, they take about 1 second, close to 47%. The main program only takes 5%. So that's all by design, and this confirms what I expected to see. But again, in a real world application, this kind of simple overview can be quite revealing. You can also zoom in on threads. Here I'm showing individual threads. You can also have ranges of threads. Here I keep it simple. What I want to do, and that's shown in red here, I want to select thread number 1, then see the function overview. Then I want to see thread number 2 and number 3. Again, that doesn't have to be a single number. It can be any sort of sequence of numbers if you want to analyze a group of threads, for example. So in this way, I can get a breakdown. I can see what happens in the various threads in my program. And this is the kind of output I get. Red is shows you that it confirms what I think it should be. There are 3 threads, and I've selected thread number 1. And this is the function overview for that thread. So I know exactly what thread 1 was doing. And as you can see, it didn't do much. It did some data initialization, calling malloc, calling a random number generator, and so forth. Thread 2, that was doing the computational work, and it's confirmed it's spending all of its time in my mxv_core function. And the same is true for thread number 3. So this profile confirms what I thought it should be. But again, in a real-world situation, this kind of information can be really revealing. And I want to stress that I didn't do anything different at the gprofng level. I just collected my data as usual. No special options needed, no nothing. I'm now going to elaborate a little bit about the filtering. I'll just show you an example where I selected certain threads. There's a lot more you can do with filters, but unfortunately the syntax is rather basic. It's not very well documented yet, so that's a bit of something we need to work on. One thing is that the upcoming GUI that I'll say more about at the end of this talk has very easy support for filters. It's really easy to use filters, so if you can wait a little longer, I would say wait for the GUI and start using the filters. They'll make your life a lot easier, and certainly the usage of those filters is extremely simple then. If you want to go and do that at the command line level, you got to be prepared to use a kind of a C-style grammar. It's working with operands and operators. For example, if you want to select everything that happens in thread number 1, you say thrid, that's a built-in variable for the thread ID, equals 1. So some more information on that. That commands, I've already shown you the threads commands. There are other commands that will give you the statistics for the experiment directory that you're looking at. And then you can have the operands, and I was just showing the thread ID, but there are other variables that you can use to make your selection. For example, you can use the sample to select a certain range in time, saying, well, I only want to look at the profile at this kind of area in time. Now, I'm the first one to admit that we need a better job, need to do a better job in documenting this. So that's noted and that's being worked on. Right now, it's a little bit bare bones. But here's an example of how you could use it. I'm setting my metrics. I'm defining my sort metric. I'm going to ask which CPUs have been used. That's already quite useful, I think. Then you can see all the threads and the breakdown of the time, as I showed a few slides ago. And I'm going to apply a filter. I'm going to define a filter that says, give me everything that happened on CPU number 11 and when thread 2 was executing. So we can see exactly what happened while thread 2 was executing on CPU 11. And I asked for the filter overview. By the way, if you want to reset the filters, because if you have multiple filter commands in your script, you may want to reset them, like back to the defaults. You define a filter called 1. As I said, the interface is a bit basic. So, but this works, and with this kind of overview, here's the this script. So this works, and this is the kind of output that I get. With the CPUs command, I see which CPUs I used and how much time they took. You can see both CPU 8 and 11 were used, and CPU 8 took used a little bit more of the cycles than CPU 11. And I've had 3 threads. We've seen this before, and this is how much time they took. And the filter command will now tell me exactly what happened on that combination of thread number 2 and CPU 11. So that allows me to zoom in on certain parts of my profile. But I can't stress that enough. Wait for the GUI if you can afford to wait a little bit longer, and that will make it a lot easier to use those filters. I want to finish with a comparison of profiles. It's an extremely powerful feature, and I want to show you by ways of a simple example how you can use that. So what I'm doing here, I'm setting up 2 experiments, running my matrix vector code on a single thread and on two threads. And what I want to look at is at last level cache misses, LLM. So I'm using an event counter called LLM with the -H option. And that will give me the value for those cache misses at the various levels that I was showing before. So I want to compare what happens when I go from one thread to two threads. Note that I don't do anything different here. I just generate two experiment directories. And now I'm going to compare. And before I forget to say that there's no real limit on the number of experiments that you can compare. You can compare a lot of them. Although in practice, that's not always easy to understand, but then you could write a tool around it, whatever. Just the fact that I'm using just two doesn't mean that we limit it to two. You can use many more. So I'm using a script, and the script is fairly straightforward. I'm limiting the output to 5 lines. I define the metrics. I only want to see the name and the last level misses. And the new element here is the comparison. So I enable the comparison by saying compare on, and I do that for the function overview because the comparison works at the function overview, the source lines, and the disassembly. So you can use that at all levels. Here I'm just going to stick with the function level. But usually what you do, once you have done that, you want to zoom in on maybe on source level or whatever. Just want to have that set because it's not on my slides. So with that script, this is the kind of output that I get. So I get a side-by-side comparison for each function, including total. I can see the number of misses, and you can do your analysis based on that. But on purpose, I picked hardware counter experiment because the numbers can be really large, and it's not always easy to even see whether there's a difference in the order of magnitude. So what we have different flavors of the comparison. And one, in this case, what you want to do is you want to compare the ratios, not the numbers. We also have a one where we actually do the difference. So you can see whether a value is higher or lower. I won't show that, but here I'm going to show you a ratio, but be aware there are 3 different things you can use in the comparison. And that's what you get with the compare ratio. You can now immediately see that the total number of cache misses drops when I use 2 threads. That's interesting, but no surprise because I'm using more cache space. So that's reflected in those numbers. So on 2 threads, I get 78-79% of the misses compared to a single thread, which is kind of nice. Init data is about the same. The random number generator spends a little bit more on cache misses, but it's so small, it's not significant. So that's how you can use the comparison feature to compare performance experiments. There's a lot more that I haven't covered here, including some more on the filters. But again, given the GUI is not that far away, maybe wait for that. You can get a lot more information on the experiments. There's more customization. The mini tutorial as part of the repo that I mentioned, the tech info document, has more information on that. And hardware event counters. I realize I didn't say much about it, but the support is there, and you use the -H option to enable that. So these are some of the future directions. First of all and foremost, we want to fix bugs. If you have a bug, let us know and we'll fix it as soon as possible. We also want to get people started. So we want to help you to get started, get your profiling job done. Regarding development, we want to make a porting guide available that if you want to port Gprofng to a different platform, that you sort of know where things need to be changed and modified. So that's one of the things we will be working on. We are working on a GUI. I'll have a little bit more on that in a second. Same for the HTML-based tool. And definitely the user guide needs a lot more information than what it currently has. Other things we're looking at, hardware counters, because we don't support all the latest processors yet. We know that's not a good situation, and we're working hard on trying to address that. I'd like to see some more metrics recorded when we do the call stack sampling. We need to have better support to attach to a running process. Currently, you can attach to a running process, but will only give you the main thread, and that's usually not very meaningful. So to me, that's a non-existing feature until we have that sorted out and you get access to all the threads of a running process. In any case, whenever you have feedback or you're interested to help, we would welcome people collaborating with us. Send it to the binutils alias, binutils@sourceware.org. That's the way to communicate with us. Those mails will be archived so other people can see it and use it as a reference. And I promise you, we're very, very closely monitoring that alias, and you will get a very quick response from us. So to conclude, some developments. I'm personally actively involved with this tool, the HTML-based output. Just want to show you what it currently looks like. Again, what we do, we take an existing experiment directory or multiple directories and generate HTML that you can load into a browser to navigate. And the main page has an overview, some of the experiment data, and then a link to the various views into it. From there, you can go to the function view. The function view has additional links to the source code, to disassembly, collies. And for example, when you click on source for something, you'll get this kind of view. And you can also go to the disassembly view down to the instruction level. And I try to highlight the parts that are taking most of the time so that you have an easy way to identify those spots. So the GUI is another thing that we're working on, and the GUI really adds value to help you with your analysis. There's a flame chart, for example, but also the timeline. The timeline shows you color-coded behavior. Every function will get a different color, and we show you how the call stacks behave as a function of time, including for multi-threaded applications, as is shown here. So you can do full analysis of the dynamic behavior of your program. You can zoom in, you can change the color, so you can literally highlight certain functions of interest. It's a great way to understand what's going on in your application. For example, what I'm showing here, you see gaps in the execution. Some threads are doing nothing. That's bad in a parallel program, and you literally immediately see that. The comparison is supported as well, so you can compare various runs, like various multi-threaded runs. You can do the comparison at the timeline level, the function level, the source level, the disassembly level. And yeah, that's all going to be in the GUI. So I hope you found this useful, give you an idea of the kind of things Gprofng can do for you and what's sort of on its way to you. So let's now have some discussions, and let's open the stage for Q and hopefully A. Thank you.
All right. So thanks a lot for this recording, but I enjoyed it very much.
You're welcome.
There has been some discussion already in the chat. So Ruud, do you want to comment on anything, on any discussions or questions that came up in the chat? Do you want to add anything?
I think we sort of covered the questions, or at least to try to answer them in the best possible way. The part where I need to explain a little bit more is that on the hardware event counters for recent processors, we are behind. There's no denying about that. We do support Skylake, for example, but AMD, we should support the EPIC architecture, which we don't. So you can't get event counters for that. You can get a basic profile. That should work, but when you go into the event counters, that's not supported, and we are aware of that. We know that that's something that we need to address. Other than that, let me see. Actually, one of the people on this call is Vladimir Mazentsev, and he knows the code from start to finish. I think he can even write it down from the top of his head. He's been working on this for a long time. So maybe Vladimir, do you know the maximum sampling rate? I know it's documented somewhere, but I don't know off the top.
No, I don't remember it.
Yeah,
I need to see code and find, but I have no access to sources now.
Yeah, and I think I got it. I think I put it in the early user guide, but I'm not sure anymore. We can look it up, but we have symbolic values for that. So you can say with the -p option, you can say high or low, and that translates to a certain sampling rate. And I'm lazy, that's what I use in practice, and I find it to work, but I understand that's not a very technical answer.
I have a question that's connected to that. What's the typical amount of data if you go with a standard sampling rate? I mean, programs could be complicated, the call stack could be very deep for each sample. So there might be some significant amount of data being collected in your home directory. So can you give a number, or is there any examples where you should reduce the sampling just to not record so much data?
Well, yes, if it's not as bad as with instrumentation where you have the traces. With traces, we all know that those files can be really, really large. It's not that extreme in Gprofng, but for sure, yeah, if you have, let's say you're running on a large shared memory machine and you have 100 threads and you set the sampling rate to very high, yeah, that will accumulate data. The biggest pain point is probably going to be when you start displaying, when we read all that information and start analyzing it. Because when you do that, there's some analysis happening behind the scenes as well. I don't have a rule of thumb for that. I'm not sure whether Vladimir has that. It's not that I found the need to run out and buy a new disk when I would do my profiling, but yeah, I can imagine that when you have a program running, we profile programs that run for hours. I mean, this is a fairly robust tool. And at some point that could be an issue, but I think in most cases we're fairly modest with the memory, the disk usage. Vladimir, do you have any rule of thumb that we can share with people? It's actually one of those other things on our to-do list to document the experiment directory, because we realize in case people would like to help out and start adding something to it, we should explain what the structure of the directory is, what kind of files are there, what they record, and that will automatically also lead to probably some rule for the disk usage. I'm sorry, I can't give a better answer than
Okay,
that.
no problem. Are there any other questions?
But again, just keep in mind, it's not as bad as tracing. I've used tracing, MPI tracing tools, and soon I would get a call from the system administrator, like why I was filling up all the disks in the system. So it's not that bad. Okay.
Are there any other questions that were not posed in the chat already? Just speak up or raise your hand.
Well, in any case, we're always available for questions. Sometimes my question latency is measured in days, not even in hours. And I realize what I wanted to ask, so don't be shy and just ask us. It will be helpful to do that on the binutils alias, but if you don't feel comfortable with that, that's okay. Just send us a mail. But the nice thing is that your question will be archived, so other people can benefit from that as well.
I actually have a list of questions. I'm trying to filter them.
Oh, okay.
So about the hardware
Yeah.
counters, what kind of infrastructure do you rely on for the hardware counters? Do you use PAPI or do you use perf? So who maintains the hardware counter support for different platforms and processors?
Well, Vladimir, correct me when I'm wrong, but that's perf events is what we use. Yeah. So I'm not sure.
So when you want to
yeah.
measure last level misses, that's something that you define, for which the mapping of this alias to the actual counters is defined somewhere in the Gprofng source code.
Yeah, right. What we have to make event counter life a little easier, because we all know it can be pretty rough with those names, is we define alias for the most common events. So like I was using LLM for last level cache misses. I'm very sure that's not the name that Intel has given on Skylake to that event. That's usually a very long and sometimes cryptic name. So we try to make that life a little easier in that sense. But you can always use the raw names. You can even use the raw code if you have that. These events always have some hexadecimal code if you want to use that. So we have some flexibility there. We also have, and again, I apologize, I realized too late that I should have added 1 or 2 slides on it. We also have an auto option that will try to give you a meaningful first set. That's for people that are completely new to this and would like to say, well, I just want to measure something, but I'm not sure what. Then we'll give you our choice for auto. That will use the maximum number of events on that platform.
Okay. What about thread awareness for OpenMP? You showed an example with Posix Threads, but OpenMP runtimes, they can take a lot of freedom as to how many threads are actually started. There could be shepherd threads. Also with MPI programs, there could be like monitor threads or progress threads. Is there any functionality within Gprofng that can be made aware of that? And which thread is actually an application thread and which ones I want to ignore?
It's on that long list to make it, as you can imagine, that's very, very near and dear to me to have improved OpenMP support. It used to be, like I said in the beginning, this tool has its roots in the Studio compilers. The Studio compilers had support for the analyzer to actually pick that up. You need to have some synergy with the runtime system and the compiler so that you can pick it up and it can tell you in terms of your OpenMP where things are happening. I still have hope that maybe the OpenMP profiling API can help us here. Maybe we can leverage that because that's a standard API for OpenMP, but currently we don't have it. You can profile, you can see what's happening, but it's rather rudimentary. It's nothing OpenMP specific, unfortunately. The best way to analyze your OpenMP program is actually through the timeline that will be in the GUI. The example I was showing actually on one of the last slides, that's an OpenMP program. And those gaps that I was showing, that was a real bottleneck that I found in that OpenMP program. And so I got around it, but yeah, we should have a little more elegant support for OpenMP. And probably need to work with the DCC community for that.
Okay. Any more questions to Ruud?
Yes, hi, maybe I have another one, or like my first one. Yesterday I played a little bit around with a thread functionality of Gprofng, and I saw when using the -threads option, I in fact get different processes with each one thread. So I was a bit confused since I was only using OpenMP. I hope it's not too specific, but like what's now the difference for Gprofng between processes and threads?
You saw different processes with the OpenMP threads?
Exactly, yeah. I was only using the -threads option, text display text -threads.
Yeah.
And I got my exclusive total CPU time, but with actually 10 different processes instead of my expected 10 different threads. Okay. So I was a bit surprised.
Yeah, me too, because it's a single process. We would have to look into that because I don't know where that could come from. Again, maybe Vladimir can tell, but I would not expect that either. We would have to look into that. Yeah, what's going on here, because it is, you don't, in OpenMP, you don't really have processes. You have a main process and that's it. So I would not expect that, no.
So in general, there's no support for different, like MPI processes, for example, right now, right?
Right, yeah.
Okay.
So yeah, if you don't mind, then we'd like to work with you and see what's going on.
Sure, yeah. I will ping you afterwards.
Yeah, thanks.
Thank you.
All right.
Hi, this is Kurt. I have one thing to say. I'd like to add that this is open source, so we'd certainly love to see others join the Gprofng community and help us deliver if you have time. For example, implementing new targets, implementing hardware events, as we Ruud was discussing, that haven't been implemented yet. Or also, we have a list of projects that we'd like to eventually add, and you may want to add to that list if you have ideas. Contributions of time can be small. I mean, we have a Bugzilla, for example. If you run into an issue like the one that was just described, you can file a Bugzilla against Gprofng, binutils Gprofng, or you can join in the discussion in the binutils mailing list, and we'd love to have you, give your info there or discuss there. So in the public. So we're trying to get things going, get a community going, and grow this. We're always happy to help you get going. We can, help you browse the code, help you find what you're looking for, guide you in any way. Vladimir is the lead maintainer, so you would work with him if you made any changes or proposed any changes, and he would approve your patch and help you get it in. So if you have any questions about that, we'd be happy to answer.
Okay, I think that pretty much wraps it up. So thank you again, all of you, Ruud, Vladimir, and Kurt, for your time. And that was very interesting. Everyone, this talk will be available in due time in our NHR at FAU YouTube channel. Apart from that, have a nice day. Goodbye.
All right. Thank you very much. Thank you.